Please start.
Okay, thank you. So like the other speakers, I'd like to thank the organizers. It's always great to come to Kyoto, and I'd particularly like to thank my friend Takenagi-san, who I know has done an incredible amount of work getting this thing off the ground, and I very much appreciate all of his work. So, whoops, don't want to give away the ending. I'll just start out by saying that this talk is going to be a little bit old school. There's not going to be any islands or JT or anything sort of, or algebras or anything fashionable like that. It's going to be basically based on trying to understand something better that in principle we've known about for quite a long time, which is the classical holographic entanglement entropy formula. Thank you. And I claim that there are subtlety, that formula has subtleties and richness to it that we still don't understand, and is worth exploring further. So the whole talk will basically be about that. So the starting point, of course, of everything of the world is the Ryutake-Yanagi formula, of course, you know, it's the foundation of so much work, and has been generalized in lots and lots of different ways, all of which are very important. In this talk, I will be talking about the generalization to time dependence, so not any of these other things, except some discussion toward the end of non-asymptotically ADS holography or entanglement. And I'll just mention that we're also doing work trying to understand the Python's lunch conjecture, and Martin, who's a Brandeis postdoc and is in the audience, can answer all of your questions about Python's lunch. Again, with you know, a lot of the subtlety there comes from when you have time dependence again. And let me just mention, before we get to the time dependence, because this is relevant for what I'll be talking about later in the talk, an equivalent way of writing the Ryutake-Yanagi formula in terms of so-called bit threads. So you have a vector field, divergenceless vector field that flows from A to its complement and is subject to a local norm bound, and that calculates for you the entropy, the area of the minimal surface, and the entropy. And this way of writing it, one of the interesting things about it is that it defines a convex program. A convex program is an optimization problem in which the constraints are convex or linear, and the objective is a convex function. And that'll be a theme of the latter part of the talk. But I also want to say something about this equivalence and about a lot of the work done on the Ryutake-Yanagi formula that to me is a little bit surprising. And the thing that's surprising is that there, in this equation here that equates this to this is a math theorem that involves essentially no physics in the sense of equations of motion. You do not appeal to equations of motion to establish the equivalence of these formulations or to establish other properties of the Ryutake-Yanagi formula. You don't really need boundary conditions. You don't really need to know what your equations of motion are. You know, anything about your matter content obeying some reasonable energy condition just doesn't enter. Okay, which is actually to me very surprising, because I mean, holography is kind of a complicated machine, and you know, presumably not just any old thing you try to do in the bulk is going to give you a healthy theory, and yet at this level, you know, that's sort of invisible. And the thing is that that's not true anymore, and things get much more interesting and more, in some sense, physical when you include time dependence. So of course we have this celebrated HRT generalization of RT. And it's already getting a little bit more complicated. Okay, so as I'm sure most people in the audience know, so here we have a boundary region A, this is my time direction, and the boundary causal domain and the causal domain of the complement. And so now we're looking for a codimension 2 extremal surface with the appropriate homology condition. This is, just a cross-sectional view of that. And already it's more complicated because in this way of writing the formula, unlike for the RT formula, we're just minimizing. First, here you have to find the extremal surfaces, and that's actually the hard part. A great advance was made many years ago by Aaron Wall, who rewrote this in a way so that you don't have to first start by finding your extremal surfaces. You simply look at the set of slices, of Cauchy slices, do a minimization on each Cauchy slice, and then maximize over the choice of Cauchy slice. And this is one of many cases in physics where having multiple equivalent ways of writing the same formula, you can think of it like the Schrodinger equation versus the path integral. When you're learning quantum mechanics, the best thing is to learn both of those, and they're useful for different things. And the best thing is actually to understand how you go back and forth between them. So this is kind of like that. Okay, and so what do we learn from these two formulas? All kinds of stuff that I'm not going to go through in any detail, but I just it's, I don't know, to me, always worth sort of pausing and appreciating just the unbelievable power that is hidden in these formulas. One thing is just, if you look at this, you might wonder whether there even exists an extremal surface with the appropriate boundary conditions, and Maximin answers that for you. It's not completely trivial fact that this actually reduces to the RT formula in the static case or the time reflection symmetric case. There's a lot of other properties, like the various extremal surfaces you might look at are space-like separated. You have consistency with boundary causality of the HRT formula, entanglement wedge nesting, and entropy inequalities obeyed by this formula. And all of these are quite non-trivial consequences, where in many cases you use one or both of these formulas. And so the whole idea of subregion duality, hinges on these properties, and these are very dynamical facts. You have to know something about the physics of your bulk to know that these are true. You have to use the equation of motion, energy conditions, boundary conditions, and if you break these, these things won't be true, and even this won't be equal to that. So this is in some ways a lot more interesting because it's strongly constraining the physics of the bulk. Okay, and that goes, of course, to the generalizations. If you want to generalize this to something with different type of boundary conditions or some different type of theory that has a non-standard holographic dual, you have to go back, or you're adding quantum corrections. Do these things still hold? And that question has a lot of power, and it contains within it a lot of constraints on how holographic dualities can behave. Okay, so let me also mention, so far those things were all things that basically had to be true for the HRT formula to be correct, and for subregion duality to be correct. But these formulas have more properties. Let's go back to RT for a second, and we know that the entropies calculated by RT have further properties that are not properties of general quantum states. The simplest of these being the MMI inequality, when you have three boundary regions, and there's actually an infinite number of higher parties starting at 5. I just wrote one of them, which is kind of maybe the prettiest and most symmetrical one, but there's half a dozen more with 5 parties, and as of last night, hundreds of 6 parties, and probably thousands that we don't know about, and so on and so forth. So, and just as a buzzword, I'm not going to talk about this. You'll hear much more about it from Veronica tomorrow, but the buzzword is the entropy cone, and that's just a shorthand for the inequalities. That's just a buzzword that means inequalities. So these inequalities, well, first of all, we don't have any systematic way of writing down the full set of inequalities. And that's sort of related to the question of what these inequalities mean. So, I mean, clearly they constrain the entanglement structure. and there have been various attempts to say what they mean in this, to say like, well, what kind of state is it that obeys this kind of this set of constraints? Like, can we say something? And so that was so in terms of this one, there's this bipartite dominance conjecture that I wrote down with collaborators a few years ago, but it, you know, I mean, even that conjecture only dealt with this inequality, and it was not obvious how you would generalize it to understand higher inequalities. And so what are we supposed to like take away from these? I mean, they're telling us something about entanglement of semi-classical quantum states, semi-classical quantum gravity states. And this is, you know, in Netta's talk, I asked this question about, you know, if you have a large amount of bulk entanglement, but it does not satisfy this inequality, then that's a counterexample to ER equals EPR. You cannot, it cannot be represented as a connected geometry. So, so they, you know, they clearly have some power, but it's like sort of unclear what we should say that we learned from these inequalities, despite a huge amount of work. And I'm not going to address that. I think Veronica will address that. But to me, a very important question when you're looking at these is whether they are artifacts of the RT formula, which, recall, has very little, in some sense, physics built into it. And so the question is whether these inequalities are valid for time-dependent states. And we know the answer for the first one. That was one of the things that Aaron Wall did with his Maximin formulation. So this one is valid for time-dependent states, but the higher ones we simply don't know. And to me, that question is very crucial because it really colors my in some sense how interested I am in the physical interpretation of these inequalities. On the other hand, of course, no one has found a counterexample despite a significant amount of work searching for counterexamples. And there are there is a limited proof by Bartek-Czech and Shidong, who proved that all of these inequalities hold in 3 dimensions. So in 3 dimensions, your HRT surface is a geodesic, and it's combinatorially much easier to, you know, talk about all the different terms. And they have a very clever proof that basically, you know, in some sense, bootstraps your knowledge of strong subadditivity to address all of the high party ones. But it requires you to be in 3 dimensions and also topologically trivial bulk. If you read their paper, they don't have that second condition, but their proof is actually only valid for topologically non-trivial bulks, and we're currently working to generalize that. Okay, so that's a question, a pretty sharp question about HRT that we'd like to know the answer to. So what I'm going to do in this talk is I'm not going to answer that question, so I should just say that right out front. But you know, the basic theme is we need more different ways of writing it. Okay, and so I'm going to give 3 ways of writing it, and they're 2 of them are related to these bit threads, and they're you know, to me, sort of aesthetically pleasing, sort of different sides of this is a coin that has many different sides to it, or whatever you call that. And so it's nice to study those. And then I'll focus on this. Oh, yeah, sorry. So as I've been emphasizing in the HRT setting, you need the dynamical information, and indeed the equivalence of these to HRT, just like the equivalence of Maximin to HRT requires that dynamical information. Although I'm not going to go through the proofs of those equivalences. And then I'll talk about 2 applications of the minimax formula, and one of them involves entropy inequalities, and the other involves non-ADS, non-asymptotically ADS spacetimes. Okay, so the first one is V-threads, and those, yeah, so they have this terminology, which is probably awful, V-threads and U-threads. The V-threads are basically the covariant generalization of the old bit threads, the RT bit threads. And the, you know, what you want to do with HRT is to make things as covariant, as manifestly covariant as possible, and sort of eliminate talking about time slices and so on. So for example, you want a formula that you know that the entropy depends only on the boundary causal domain of A, not on the particular choice of time slice for A. So there's a time slice A here sitting here, and we kind of don't want the formula to depend on that. And so it makes sense if you're going to have something like the flow field, it's going to be, you know, a divergenceless vector field in the bulk, and you're going to be interested in the flux over the entire D of A. So we get rid of the dependence on A, and now it just depends on D of A. And the threads which are just the flow lines of this V, of course, you want them to basically begin on D of A and end on D of A complement, so you don't let them end on singularities or on other parts of the boundary or past and future infinity. And this part somehow I think is like hopefully, you know, not a big leap from the RT bit threads. All I've done is I've just added the time direction, extended A into D of A, and that's kind of it. The hard part is the norm bound, which for the regular bit threads or flow field V is just a simple local norm bound that the norm of that vector is less than or equal to 1 everywhere. And it's more complicated here, and that's because you've stretched things out in the time direction. And so the constraint becomes a non-local constraint where for every time-like curve, you have this, the integral of the perpendicular component of V. So basically, you should imagine an observer who is traveling on some time-like curve and is counting the threads, okay? And it's not a bound on the density of threads at any given time, but on the integral over the observer's world line of the density of threads. And that is kind of the stretched out in time version of the regular bit threads, okay? And this thing does define a convex program, although it's a little bit awkward. I mean, I think this is kind of intuitive, but it does have the disadvantage that it's non-local. And if you wanted to check it, like if you wanted to throw this thing on a computer, which, you know, computers are great at solving convex programs, it would be annoying because you have to check this thing for every single observer, right? And so I just want to say that, and I'm not going to go through this in any detail, but this can be rewritten as a local constraint, a pointwise constraint, but at the cost of just adding another degree of freedom, which is a clock function. Okay, so that's your program, and then what you find is that the solution to this program, that an optimal, just like an optimal flow field in RT, finds the RT surface. That's where the vector field hits the norm bound. Here it's even stronger. It finds the HRT surface. All of the bit threads have to go through the HRT surface, and it discovers the entanglement wedges. Basically, the vector field has to, in an optimal configuration, has to vanish in the future and past of the HRT surface, and it's non-zero only in the two entanglement wedges. And morally speaking, I mean, I'm not going to go through this story again. I've given countless talks on bit threads and so on, but the idea is that they're supposed to represent bell pairs in some entanglement distillation of the state. Okay, so those are the V threads, and then there's another formula which does not have an analog in the RT case, which are these time-like threads. So now actually we're gonna change our point of view, and we're gonna be interested in again a divergenceless vector field, but now a time-like one, and it's gonna have the complementary boundary condition that it's only allowed, the threads are only allowed to end on the complement of D of A and D of A. In other words, they're not allowed to end, whereas the V threads had to begin and end on D of A and D of A complement. With the U threads, it's the opposite rule. And now it's a minimization thing. You're trying to minimize the number subject to a norm bound, but now the norm bound is actually is an integrated norm bound, but now for curves, for space-like curves connecting D of A to D of A complement. So it's not about an observer anymore. It's about kind of adding up the total amount seen along a space-like curve that connects D of A and D of A complement. And the objective is just the total flux. By this constraint, you can measure the flux anywhere. So even though there's a slice in the picture, the choice of slice is irrelevant. It's, you know, one way to think of it is to think of this lower bound on the norm is that the threads are creating a barrier. you're trying to build a wall that separates D of A from D of A complement, and the wall has to be a certain height, basically, which means there's a certain amount of obstacle between them created by these time-like threads. Again, this somewhat awkward non-local constraint can be written as a local constraint. And then the optimal configuration is just the complement of what was on for the V threads, where now, as with them, all the threads go through the HRT surface, but now they don't touch the entanglement wedges. Again, it's a convex program, and if you know about convex optimization theory, it's a Lagrange dual of the previous program. Lagrange duality is just like duality in physics, where you have two equivalent ways of writing the same thing. So that's the relation between these two guys. And one thing that happens under Lagrange duality is that the constraint and the objective kind of get switched with each other, and you can see that here. This is the back to the V threads, and the constraint is enforced by time-like curves, and the time-like curves are the objective. That's the thing you're trying to minimize on the U-flow program, and the constraint on the U-flow program was actually V threads. This norm bound is enforced by curves connecting this boundary to this boundary. So the objective and the constraint have just swapped places in these. And I said that the V threads morally are bell pairs, and so if you want words, if you like words, the U threads, it can be thought of as disentanglers. You're asking what's the fewest disentanglers that you can do that will actually completely disentangle A from A complement. I mean, this is just strictly some kind of hand wavy thing. I don't have anything more precise to say about this. I'm just saying it matches the counting, which may be meaningful or may not be meaningful. Okay, so that's those are the bit thread analogs, and now I want to talk about Minimax, which you might guess is just swapping the order of the minimization and the maximization from maximin. So what is it that you're supposed to do? Okay, so what you do is, instead of talking about slices, so this is going to be completely slice-free formula, okay? But we need something that we're doing the minimization with respect to and the maximization. And in general, in maximin, the maximization is always with respect to variations in the time direction, because if you make it wiggly in the time direction, the area goes down, and the minimization is with respect to spatial variations. And so what's going to happen is the surface is going to sit on a timesheet, which is a time-like hypersurface, okay? And we're going to, within the timesheet, we're going to maximize, we're going to look at find the maximal area surface, and then we're going to minimize over the choice of timesheet. Okay, so there's a bunch of things to be said about this. The first thing I'll say is that you might wonder whether it's innocuous to switch the maximization and minimization. So if you just give me a function of two variables, the max with respect to one variable, the min with respect to the other, versus doing it in the other order, it doesn't give the same answer in general. Okay, and in fact, there's actually, I discovered there's like a whole field of math which is just dedicated to the problem of knowing under what conditions they are equal. And the reason there's a whole field of math about is that essentially game theory boils down to this this question, and so economists are very interested and so on. And so so there's like but in this case, again, in this, like, there's a proof where we invoke the Einstein equation, we invoke the null energy condition, and so on, to say that indeed we can switch the maximum and the minimum. And by the way, if you don't, we also give counterexamples in the paper where it doesn't work. If you don't impose those conditions, then it doesn't work. It's not true that these quantities are equal. So there's a lot of physics in the fact that you actually are free to do this swapping. Okay, so what's going on with these timesheets? So one of the things that I think is very nice, in fact, I would say like the main cool new thing about Minimax compared to Maximin is that it changes the homology constraint. So normally we're used to thinking of homology as being enforced on on a slice, like in RT or even in Maximin, you have a slice and then you do a homology condition on the slice. And this is, as I said before, this is completely slice-free. And the homology condition is a space-time homology condition. So it's saying that this timesheet has to be homologous not to A, but to D of A. So actually, I probably should have just gotten rid of the A and just written D of A, because again, it doesn't matter at all what A is. It just has to be homologous to D of A relative to basically the rest of the boundary. Okay, so basically the timesheet has to sit between D of A and D of A complement. And that leaves it a lot of freedom to wiggle around. So for example, it can meet the boundary somewhere. It can even hug the boundary of D of A, and so on. So you have a lot of freedom in how you do where you put the timesheet. Yeah, so it's floppy. And then from this point of view, you can actually redefine the entanglement wedge. So normally the entanglement wedge is defined that you have a slice because you've just finished doing Maximin, and then you look at the causal domain of that part of the Cauchy slice, of the homology region on the Cauchy slice. Here that never appears. There's no slice. There's no causal domains. It turns out to equal the smallest homology region. So if you push the timesheet as close as possible to D of A, then you will capture the entanglement wedge. And then a lot of the properties they gave, like wet nesting and so on, you can prove in this formalism. It's just just gives you a different viewpoint. Okay, so that's Maximin, that's Minimax, and what can we do with it? So I'll give two examples. They're both work in progress. Let me say it that way. Okay, so let's just go back to RT and recall that if we fix a set of boundary regions, we can turn our bulk geometry into a graph. And so we can discretize it. And the way to discretize it is along all of the RT surfaces, which cut each other up and leave behind these cells. And if we associate to each part of an RT surface an edge of this graph, so each cell is going to be a vertex, each edge is going to be a partial RT surface. We associate to the area of that the weight of this edge, and this discretization, it just sort of captures all of the information in the in all of the different entropies. So if this is like A, B, C, D, you could learn from the graph, S of A, S of AB, S of BC, and everything else. So it just is a way of packaging the information about those entropies, which is just a handy mathematical trick just mainly in the sense that a lot more is known about graph theory. You turn it into a graph theory problem, and then people have studied min cuts on graphs, and you've turned the problem into that. Okay, I mean, there's not really much more content to it beyond that. But what it says is that the whole story of the entropy inequalities in the entropy cone can be turned into a question about min cuts on graphs. Okay, so in some, if you want to talk to a mathematician who studies min cuts, like most likely they will be a graph theorist, and they will not want to hear about Riemannian metrics. That's like too confusing and continuous for them. So you discretize it, and then you can talk to them. Okay, and they can use combinatorial thinking. Okay. And then also there's there's the fact that maybe this, and I didn't write these words on the slide, but I'll say them, that this kind of looks a little bit like a tensor network, and in fact that can be made more precise in certain cases where you can actually where it actually is a tensor network. Although so far it's unclear how general that is. Okay, so can we do the same thing for HRT? Now, this is not obvious because HRT is not just a min cut problem anymore. And when I say we want a graph model or desiccation, what I mean is that we have, again, a weighted graph to which you can apply min cuts. Okay? It's not at all obvious. In fact, my entire life, up until a few months ago, I assumed it was not possible, just because it's not a minimization. In the RT formula, you're not doing in the HRT formula, you're not doing a minimization. And so why would you be able to encode those entropies as a min cut on some graph? Okay. And it's very related to the entropy cone and the entropy inequalities, because if you can, then you have the same entropy inequalities, because as I said, those are essentially properties of graphs. Okay. But I also think, even apart from the entropy inequalities, that this is just a very interesting question in itself. Also, because of the tensor network point of view, it would kind of say that you would have some tensor network that essentially wouldn't care about the time direction. Okay. I mean, the time direction in HRT is playing this role of a spoiler. It's kind of ruining everything that was nice and beautiful in spatial geometry. Okay. So can we recover some of that? The idea is to use timesheets to try to address this question. And so the first observation is that when I have multiple boundary regions, so I mean, in this picture, I really should have drawn entanglement wedges and stuff like that, but it gets too cluttered. So here, imagine at some time on the boundary, I've divided up that boundary slice into like A, B, C, and D. Okay. And then I have a timesheet for each of those. And let me just look at, just to avoid cluttering the picture, the timesheet for AB and the timesheet for BC. And so maybe this guy, yeah, so here's the top view. And so tau1, tau2 is the timesheet for AB, and tau3, tau4 is the timesheet for BC. And they cut each other the same way that RT surfaces do. And that's actually the key, because what HRT surfaces don't do is cross each other. They generically, they miss each other. They don't sit on a common slice. And so at least from this top view, it looks like we've kind of gotten rid of that problem, because indeed the timesheets cross each other. Of course, that's too quick. What's the actual content here? So what we need to do is look at what these surfaces are doing. It's not enough, of course, to know what timesheets are doing. You have to look at what the surfaces are doing, and the surfaces also get cut up. So like gamma 1, gamma 2 would be the HRT surface for AB, and gamma 3, gamma 4 would be the HRT surface for BC. And always in these entropy inequalities, we just want to know what's going on when we have these like overlapping, sets of regions. Okay, so there's a property that these timesheets can have, which we call cooperating. And cooperating means basically, so you know that since this is the HRT surface, it's maximal on its timesheet, the green timesheet. But it doesn't, now if I cut the green timesheet in two, is the part on one side maximal within its partial timesheet? That's the key property, which we call cooperating. So that depends on arranging both of the timesheets appropriately with respect to each other. Okay, so cooperating means that every partial HRT surface is maximal on its partial timesheet. Okay, and we have a conjecture that there exists for any choice of boundary regions, there exist cooperating timesheets. Okay, so if some of you, if you've heard versions of this talk in the past, this was stated as a theorem, and normally you're supposed to go from conjecture to theorem. And here we've gone the wrong way, and that's basically, we discovered some subtleties in the proof we had, and it turns out actually to be very far from trivial to prove this conjecture if it is true. So we're kind of in the midst of that. But why should you care about this? Why do we care about cooperating? So basically, if you have a cooperating set of timesheets, you get yourself a graph model. Okay? But what you've done, again, this is slice 3, what you've done is you've decomposed the bulk space-time into cells. So every vertex is a bulk cell, and every edge is a partial timesheet. It's a weighted edge, and the weight is the area of that gamma I, the partial surface on the partial timesheet. Okay? And you can convince yourself that if you have cooperating timesheets and you build this graph, the min cuts on the graph. So basically from there, you don't have to do any max. It's just min, okay? Will reproduce all of the HRT entropies. Okay, that's a very simple thing. I mean, it's probably not helpful for me to go through it, but it's a nice exercise just to convince yourself that this cooperating condition implies this. And once you have a graph, you have the same entropy cone. You have the same inequalities. Okay, so if this is true, then indeed the entropy inequalities are the same because you've got yourself a graph. Okay, yeah. So
Definition of cooperate, if every partial HRT surface gamma I, for example, gamma 1, is maximal on partial times C tau 1 with the central point also fixed?
No, so
No.
that, well, no, in fact, I mean, neither endpoint is fixed. So you just have to find the maximal surface on this whole, the maximal area acausal surface on this whole thing. So you don't know, when you're looking for these cooperating timesheets, you don't know where to put the intersection, and everything hinges on putting the intersection in the correct place. I mean, as a simple, like, why is this a sensible thing to even consider? Basically, if you want gamma 1 to be maximal, then it had better be the case that it intersects the seam. The seam is where these two things intersect orthogonally, because otherwise you could just move it up and down. And so you better arrange it so that the angle there is orthogonal to the HRT surface. So that's something you can do. And so if you look at sort of simple situations like that, you see that you can do it. Okay, but then in more complicated situations, we haven't quite figured out like a general proof that you can do it. But we haven't found like a counterexample yet. One thing I want to say, okay, so actually what I should have done here is restrict your attention to the Wheeler-DeWitt patch. So the cells are not really parts of the entire space-time. I mean, stuff could be happening, 100 years from now, after you're done with your ABCD, that changes the bulk. That's irrelevant. That doesn't enter into these cells or this graph decomposition or whatever. So really, you look at the Wheeler-DeWitt patch, and it's the Wheeler-DeWitt patch that has been decomposed into cells, into space-time volumes. Okay. Okay. So I think this leads to very interesting implications if it's true. And I mean, one reason why I have some optimism is that of course, we know that strong subadditivity and MMI are true. And so they should have some proof in terms of minimax. And, this seems like a really clean way to prove them using minimax. And so it kind of gives me some optimism that this conjecture is true. But that being said, it's a logical possibility that the conjecture is true when you just have 3 boundary regions. And as soon as you have more boundary regions, which you would need for the higher entropy inequalities, it's not true. Right. So I mean, that may happen. Okay. 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 How am I doing on time? Okay. I mean, I'm well aware that I'm the only thing standing between you and lunch. So I'm gonna try not to go over here. Okay. So one of the things that's nice about minimax is that it changes the homology condition. It refocuses your attention away from slices to space-time volumes. Okay. And I think that has a nice application. So I'm going to make a few conjectures, which are not, I mean, the first couple are sort of special cases of things that people have said, like it's related to Tadashi's surface state correspondence and so on. But anyway, so we know that if we have let's say a 2-sided black hole with asymptotically radiated black hole, that that geometry represents entanglement between the 2 boundaries. And that the amount of entanglement is given by the area of the HRT surface lying somewhere in there. I think it's reasonable if you have an asymptotically flat space-time that should have a Hilbert space of quantum gravity in that space-time, and that if you have 2 of them with an Einstein-Rosen bridge, that would represent each one would have a Hilbert space, and this space-time would represent entangled pure state of them. And somewhere in the middle, there should be an extremal surface that calculates the amount of entanglement. And similarly, if you have asymptotically de Sitter, I think it's, I mean, again, yeah, Dio asked, like, is it one-dimensional, infinite dimensional, or what? So I don't know, but the Hilbert space for de Sitter, I don't know. But let's say there is a Hilbert space for de Sitter, and then this, I think, is a entangled pure state of the two de Sitters. And of course, you can do more complicated things. I mean, you don't have to have the same. You could have flat on one side and de Sitter on the other if there's a domain wall where the cosmological constant changes and so on. And again, in there, there'll be an extremal surface. So this is a pretty mild generalization of the HRT formula. But if you start to think about, okay, how do I define this? And to do it in as generally as possible, and you're going to need to impose some homology condition. The space-time homology condition is the way to go. Oh, sorry, I forgot to put that up. So, okay, so these are some conjectures. Each universe has a Hilbert space. These represent entangled universes, and the entropy is given by the area of an extremal surface. And I think the best way to define, at least I think the cleanest way to define this surface is via minimax. And so where, again, you impose a space-time homology condition on your timesheet against an entire boundary. So you don't have to worry about slices. I mean, this guy, like, where would you anchor your slice if you wanted to do maximum? Maybe you could anchor it up here, but then if things are more complicated, like you have multiple black holes, you'll get into trouble if you do that. Here, you could anchor your slice here at scry naught. But I think with the timesheet, you just say, well, take the entire asymptotic boundary. And that's the thing that you should be homologous to, that your timesheet should be homologous to. And this is homology. You have to do it relative to the singularities or end of the world branes or other stuff that you have in the middle that doesn't represent asymptotic regions. I mean, this can be generalized. So you're going to have a whole network of universes. So here, each red dot is a universe, an asymptotic region that has some asymptotic boundary conditions. And the green dots are wormholes that can be like a two-sided wormhole. So this is a universe that has 3 black holes in it, each of which is connected to another asymptotic region or multiple asymptotic regions. This is like a 5-boundary wormhole. Anyway, so in this setting, and here again, it's a mild generalization because I'm not trying to, I think the hard part in these generalizations, which people have tried to do, is say, what if I have a part of this de Sitter asymptotic boundary? What if I have a part of this? So I'm not brave enough to do that. I'm just doing the cowardly thing and just talking about entire asymptotic region. So I'm the entanglement entropy of this entire guy, and this entire guy. Okay, that I think is pretty doable. And again, it's just cleaner to do it in terms of space-time homology. And now I'm in the red, so I'm done. Thank you.
Question or comments?
Matt, I had 2 related questions related to the cooperative timesheets. So I was hoping, could you reiterate what the current status is of the entropy inequality proofs using timesheets? Like, is your understanding of cooperative strong enough to go ahead and prove MMI, or is that still open to question?
It's still open to question.
Okay. And then can you also maybe explain a little bit?
I think we have SSA.
Okay. Can you also explain maybe a little bit about what the difficulty is in proving the existence of cooperativeness? Presumably has something to do with like intersections of multiple timesheets.
Yeah, exactly. Yeah. Exactly. So, so at the place where, so basically the putative counterexamples are situations where the HRT surfaces are themselves intersecting. I mean, the problem may go beyond that. Those are just, maybe if they're separated, you still have a problem. But certainly for those, what happens is you start to put what seems like too many constraints on the timesheets. In the cases where we've been able to really study it carefully, it wiggles out of those. I mean, you have a configuration, you're like, there's no way you can make a call. You just have too many constraints. They're contradicting each other. And then you start using global knowledge that, oh, these HRT surfaces are actually reaching the boundary. It's an ADS space-time. And when you put that information in, it kind of manages to just barely obey the constraints. But it's like, so far, it's like case by case. And so if this theorem is true, we would need a some kind of different proof strategy, basically.
So can I ask a question about, you have two bit threads, U and B. I'm very curious about the vertical one. So
yeah, the time like one, yeah.
Disentangle, you mean this unitary transformation and the time evolution? What kind of tensor network picture do you have in mind? I mean, usually one way to understand tensor network is a space-like slide.
Yeah, yeah.
And that is a tensor network. But
Yeah.
maybe you're thinking many layers of tensor network, and they are connected by your disentangler, or
yeah, I have not tried to make this precise, but I think I would sort of take the collection of threads as this, maybe the gates in or the tensors in a tensor network, and I would not try to think of it as some kind of time dependent. In other words, in some sense, the point of them is actually to project out the time direction and to sort of forget about time. Once you have the set of threads, you kind of forget about the fact that they're extended in time, and you forget about the time direction entirely. So, I mean, if I had to make a guess about how to turn the U threads into some tensor network or disentanglers or something, I think, and this also is with the graph model, by the way. The idea is that you having done the graph model, you forget about time, which is the thing that's causing all the trouble in trying to make a tensor network and so on. But I don't really have anything more precise to say.
Thank you very much. I ask more.
It's about these U and V threads.
Yeah.
So what is the issue with putting a local constraint saying that the density should be less than 1 or greater than 1 for U threads?
Right.
Why do you require a integrated non-local constraint?
Yeah. So maybe that's easiest to study or to think about in the V threads, that essentially one way to think about them is that if you had threads on a slice and then you spread them out, then you under that operation of spreading them out in time, it's really the integrated density that gets conserved as opposed to the density at any point. So the density, if you put them together all on one slice, which you could do, so there exist optimal, I mean, maybe I should have said this. There exist optimal configurations where actually all the threads are on a single slice. The density is infinity. I mean, there's like a delta function of density there. So you don't want to rule that out. That's totally fine. But so that it's because it was born as a smearing out in time that that the appropriate thing is an integrated density, if that makes sense.
In this problem, the U or V threads, is the constraint always saturated on the solution?
Oh yeah, so it's saturated on the surface. So that's the same as with the regular RT threads, that they saturate the norm bound on the RT surface. And indeed here, that's the only place for generic configuration where the density bound is saturated for both U and V threads is actually on the HRT surface.
Any other question?
So does this coherent generalization of this thread also apply for multi-thread?
Oh, I haven't thought about covariant. You mean these threads that have like branch points? Yeah. Okay. So there's two things. I'm not sure which one you're referring to. So one is if you have multiple boundary regions, you can have threads like connecting A to B and B to C and A to C, and it was thinking about those that we proved MMI using bit threads. So indeed, you can do the same thing with these. At least you can define them. It's actually harder to prove things. So we don't have a covariant proof of MMI based on these. Then there's another thing you can do, which I guess are called hyperthreads. Is that right, Jonathan? Where you let the threads split and so on to represent multipartite entanglement. I haven't thought about that. I mean, I don't see any obstruction, but yeah.
Any other question? Last question.
So these inequalities that apply only holographically and not for general things, do they apply only in Einstein gravity, or if you retreat, you go away from the large lambda limit, do they continue to apply? just in the time-independent case?
Yeah, that's a subtle question. So the first thing I would say is, really, you should treat those corrections perturbatively, and because it's sort of an effective field theory in the bulk. If you try turning them on like Gauss-Bonnet corrections a finite amount with either sign, you violate causality. So that, and if you're only doing it perturbatively, then the inequalities are kind of, they're only affected in situations where you are saturating them at lambda equals 0. And those situations for RT are kind of robust in the sense that small changes in your formula they'll still be saturated. It's never going to kick you into the violated direction. That being said, all that being said, if you're brave and you say, you know what, I'm going to add like a Gauss-Bonnet correction with a finite coefficient, at least for a Gauss-Bonnet thing, because basically when you look at the proof using RT, which is just a cut and paste argument, as long as the functional you're looking at is extensive, and the Gauss-Bonnet terms are extensive, and therefore the proof will go through for them. But for other more complicated things that are not Gauss-Bonnet, it's very unclear.
What is your suspicion? Large but finite lambda?
Yeah, so we have some evidence that they do, from what I just said. Another piece of evidence is that if you're doing a 2D CFT, you can calculate it just from the boundary. You can calculate your entropies just from the boundary. And those entropys that you calculate just from the boundary do obey these inequalities, regardless of the, I mean, it's basically a large C thing. It has nothing to do with the, even if it was a free, large C theory, it would obey the inequalities. So I think that's kind of the evidence that I have that probably they are. I mean, my suspicion is basically this whole entropy cone story is a large N thing and does not require strong coupling. I mean, you would first, I would first want the free theory, but I suspect that that's true. Yeah.
Okay, so let's thank speaker again.
Thank you.
Is there announcement?
So those who will give poster presentation, please help us to bring some poster boards to Mass Cover Hall. And also you can set up your posters this lunchtime.
Next session starts at